Okay, some more problems from 9.5. This is number 17, and again, we're still trying to show whether these series converge or diverge and state the method by which we're going to use. So we'll take a look first of all, or the method that we are going to use. Okay. First of all, we'll look at the nth term. We'll look at this limit, because this is always, you can examine this limit, and if it goes to any number except for 0, then it diverges. That's the nth term divergence test, or the nth term test for divergence. And let's take a look at this limit and see what we've got. So we can take a look at this limit as n approaches infinity, and we can intuitively state that as n approaches infinity, we can drop the 1, so we can look at this. And basically, it's the same as n approaches infinity. The top number becomes insignificant, all right? We could use L'Hopital's rule, but then we're just going to have some extra terms that kind of clutter up things, but it would still also work. It would just make it a little bit tougher. But intuitively, you can say that that goes away. All right, then we could also then just separate this into 3 to the n times 3 to the negative 1, all over 3 to the n, and the 3 to the n's would cancel. So we end up with a limit of 3 to the negative 1, which is the same thing as 1 over 3, and the limit as n approaches infinity of 1 over 3 is just 1 over 3. That's not equal to 0. So therefore we can say that this series diverges by the nth term test for divergence. Okay? All right. Okay, let's take a look at number 18. I hope that makes sense. Now you could use L'Hopital's rule, and then when you multiply these out, then you would have a lot of canceling the same way. But I didn't really want to spend that much time to do that. But it would also work the other way. We'll show you L'Hopital's approach, I think, momentarily. Okay. Now let's take a look at number 18. So this is an alternating series. These are always good to check. Again, we can look at it real quick, and we take the limit of this as n approaches infinity. That's going to be 1 over infinity to 0. So we're not going to have a divergence there. You can check that out pretty fast. So let's let u sub n equal 1 over the natural log of n. For n greater than or equal to 2, u sub n, is that greater than 0? Yes, it's always positive. Is it decreasing? Yes, I keep getting these bigger. This is going to make the denominator is going to get bigger, so the fraction will get smaller, so it's decreasing. And we just said the limit as as n approaches infinity of u to the n, that's 1 over infinity, is going to be equal to 0. So that's all we have. So therefore it converges by the alternating series test, or the AST. You can call that AST. So as long as it meets these three criteria, and it's an alternating series, for an alternating series, it converges. And that's sometimes called the Leibniz test. All right, so sometimes you'll see the Leibniz test written down. Here's number 19. Now we've got to go back and kind of review some of the things we did in chapter 8, and some of these things are just, and we mentioned a little bit that this when we were talking about some of the Lagrange examples in 9.3. Okay, but if we look at this is an alternating series, but just look at the nth term. I have 10 to the n over n to the 10th, all right? And we want to find the limit of this a sub n. Well, we have to remember from 8.3 of the growth rates, okay, from the slowest to fastest as x approaches infinity, the slowest would be the natural log. Then x as a base would grow faster. Then x as an exponent would grow faster. And the fastest is the factorial, x as a factorial. So this is back from 8.3. We talked about this, and I think we might have given you a little chart of this. But if you look at this, this goes the slowest, okay, the natural log of x, all right. X as a base grows faster. A to the x grows even faster, and factorial. Now you can graph all these on your calculator, and you can see that at first, as we get maybe 1, 2, or 3, or 4, the growth rates are kind of jumbled up. But as we get bigger, you'll see eventually, as you start to get past like 5 or 6, then you'll see that this goes up even at a steeper rate. They all start very gradually. Now the natural log goes like this, but then this is an exponential, or this is a kind of a parabola type function, and this is exponential. And then the factorial starts out a little bit slower, but then eventually it starts going real steep. So if you check that on your calculator, you'll see that this is the slowest, next fastest, and by far the fastest. All right, so factorial. So when I look at this, I got 10 to the n. I've got n as a power over n as a base, so this will grow faster. If the top grows faster than the bottom, as we go to infinity, the limit is infinity. And that's back from section 8.3. If the bottom grows faster than the top, then it will be 0. So in this case, I've got 10 as a base and n as a base, n as a power. Power grows faster than base, so it's going to be infinity. So therefore, we can say that this diverges by the nth term test for divergence. So you might want to write that down if you don't have it down on a card, so you know about your growth rates, because we need to use these as we do these series problems. Okay? Hope that makes sense. So the nth term test for divergence, it does diverge. Okay? Take a look at number 20. I put a little bit extra stuff down here, just if it wasn't intuitive to you, so it maybe make a little more sense. Again, we have an alternating series, so I have to check the limit anyway, as n approaches infinity the nth term, and we'll check that out. So first of all, is it greater than 0? Well, if n is greater than 1, n goes from 1 to infinity. For n greater than or equal to 1, that's going to be positive, that's going to be positive, so it's going to be greater than 0, that's no problem. Is it decreasing? Well, you could look at it intuitively, and you could say as n gets bigger, the bottom is going to get bigger faster than the top, so it is going to be decreasing. But we'll show that in a moment. And then is the limit as n approaches infinity 0. You could look at this, and you can kind of intuitively take care of the ones, and you can see that the bottom is going to grow faster than the top, so because we're talking about the square root versus the number. But we'll show you that in just a second anyway. So, but we can intuitively say that the limit as n approaches infinity is 0. So it looks like it's going to satisfy all 3 steps for the Leibniz or the alternating series test. So therefore, it's going to converge. But let's just kind of show you some other ways to do this. Let's say we weren't too sure and we wanted to show that this was decreasing for all n. So we would just take a look at this function, f of x equals x plus 1 over x, the square root of x plus 1 over x plus 1, and let's take the derivative and show that if the derivative is negative, if it's always negative, that means the slope is decreasing. That means the value of the function is decreasing. So that's another way of doing it. So we can take a look at this function, square root of x plus 1 over x plus 1. We'll take the derivative, which uses the quotient rule. Okay, that's not too bad. Low d high, and that's just going to be 1 over 2 times the square root of x. Let's high d low. High d low, the derivative of x plus 1 is just 1. Denominator squared below. Then I can multiply the top and the bottom by the 2 times the square root of x to get rid of this denominator. And then that's going to cancel, so I got x plus 1, then I've got negative, and then that's going to be 2x, because the square root of x times the square root of x is x, and a negative 1 times that is going to be a negative 2 square roots of x all over this. All right? And then we can simplify this a little bit. This would be x minus 2x is negative x. I got 1 minus x minus 2 times the square root of x all over this denominator. Well, this denominator, for x is greater than 1, all right, this denominator will always be what? Positive. And the numerator, since this will be positive and this will be positive, and I'm putting negative signs in front of them, will always be negative. So that's a negative for all x greater than 1. All right? So the function is decreasing because the derivative is always negative. All right, so that could kind of be another way of verifying part 2. Okay? When x is 1, I do have, actually I could say probably less than or equal to, because when x is 1, this is still going to be positive in the bottom, and this would be 1 minus 1, which is 0, and negative 2 times 1, so actually we could always say less greater than or equal to 1. And that would be fine. Greater than or equal to 1. Put a little equal sign there and we'd be okay. Sorry about that. I hope you can see, get that in, but that's good enough here. I'll get a pencil to put that in. Okay. And then if we want to check the limit, if we want to take the limit of this, and we can use our good old L'Hopital's, we take a look at this. This is another way you could do this. If I put the limit as n approaches infinity, that's infinity plus 1 over infinity plus 1, which is infinity over infinity. So I can use L'Hopital's rule and take the derivative, and the derivative of this is going to be 0, and then 1 over 2 times the square root of n, and then the derivative of this would be 0, and the derivative of that would be 1. So I just have this limit, and the limit as n approaches infinity, that's 0. So that's another way of doing that. So therefore, after all is said and done, on number 20, the series converges by the AST, the alternating series test, or by the Leibniz test, if you want to use that. Okay? Hope those help.